This video explains the ICLR 2025 Spotlight paper, The Computational Complexity of Circuit Discovery for Inner Interpretability. Its main contribution is not another heuristic, but a formal map of which interpretability queries are computationally feasible and which are provably hard. Many promises of mechanistic interpretability assume we can find faithful circuits at scale. But if the underlying query is intractable, failures of heuristics may reflect hard limits, not just poor engineering. This paper makes that distinction formal. Their conceptual scaffold organizes circuit queries by affordances, description and explanation, plus prediction and control. The key idea is to ask not only what a circuit is, but what operations it enables. They systematically generate query variants along key axes: local versus global coverage, bounded versus unbounded size, and minimal versus merely sufficient constraints. This turns an informal literature into a clean computational design space. Methodologically, the paper combines classical and parameterized complexity. Classical results classify tractability in polynomial time, while parameterized analysis asks whether hardness disappears when model or circuit parameters are small. Formal results are developed on multi-layer perceptrons, treating each neuron as a unit. This is chosen as a rigorous starting point and still relevant, because MLP blocks are central to transformers and many modern networks. A key query family is sufficient circuits. Given a network, an input context, and a size budget, can we find a subgraph that reproduces the target behavior? This formalizes the common, pruning-style interpretation objective. Core result: many circuit discovery queries are intractable. They prove NP-hardness and even higher hierarchy hardness for variants of practical interest. So exact scalable discovery is often not expected in the worst case. Crucial nuance is fixed parameter intractability. For several queries, hardness persists even when constraining model or circuit features like depth. So keeping networks shallow does not automatically rescue tractability. They also study approximation and show strong inapproximability for hard query families under additive, multiplicative, and probabilistic schemes. That means even approximate faithful circuits can remain computationally out of reach in the general case. An important theoretical separation emerges between local and global queries. Local variants can be substantially easier than global variants. This gives a formal lens for interpretability illusions where local behavior looks faithful, but global faithfulness fails. The paper is not only negative. For some local hard queries, they prove NP completeness, which enables reductions to better understood hard problems such as satisfiability. This opens practical solver-based routes. Another positive path is quasi-minimality. They define a relaxed circuit notion that retains useful affordances while sidestepping some hardness barriers. This leads to tractable queries and efficient algorithms for selected tasks. Beyond sufficient circuits, they analyze families such as necessary circuits, patching-style control queries, and robustness-style redundancy queries. A recurring pattern is that expressivity and strong affordances often increase computational cost. Methodologically, the strength is systematic coverage. They formalize a broad query language, prove results across many variants, include parameterized and approximation analyses, and provide a shared reference table of complexity outcomes. For practitioners, the message is operational. Match your interpretability objective to complexity-feasible query variants. Prefer local or quasi-minimal formulations when global exact faithfulness is infeasible, and leverage solver transformations where available. Limits remain. Results are developed for MLP circuits, so transferring exact complexity boundaries to all modern architectures requires further formal work. But as a foundational map, this substantially advances what questions we can ask responsibly. Open problems include extending this framework to richer architectures, refining average case analyses, and designing complexity-aware benchmarks that directly test local-global faithfulness gaps in practice. Final takeaway: this paper reframes circuit discovery as a complexity-constrained design problem. Rather than asking only whether a heuristic works, we should ask which query class is computationally viable, what affordances it preserves, and what faithfulness guarantees are theoretically possible.